Hello, welcome to the introductory video about current and resistance. The reading in this section is chapter 27, and it's 27.1 about electric current, and then, oops, sorry, I used the wrong control there. 27.1, and then 27.2, which talks about drift speed and current, which we will talk about in a minute. 27.3 is very important, this is Ohm's law, which we're going to be using a lot in the next month or so. And then we move on from there to talking more about resistance and looking at something called resistivity. We're going to talk about all these things as we go along. And after that, we're going to look at what happens to resistance and temperature. And then beyond that, we look at something important, electrical power, which has a lot of examples. But first, I wanted to talk about current. And really talk about it. You can see here, it's the amount of net charge passing through a surface per second. But I want to talk less about the definition and more about what it actually is. Current is the transfer of the movement of electrical energy, and it uses charges. Now, by convention, of course, it's the direction a positive charge would move, as we've had with electric fields and electric potential. But it's really electrons moving through conductors. A lot of times people will describe this as analogous to water moving through pipes. And in some ways it's similar to that. But the problem I have is a lot of students picture an empty pipe and water suddenly rushing through that pipe and filling it up as it goes. Well, that's not really how it works. The water would have to already be in the pipe, and the molecules of the water would transfer the energy more by bumping into each other than following along after each other. So I wanted to show you one kind of neat little animation here. The wire part is kind of hard to see. It's this gray box on a black background. The little red dots are your charges, they represent positive charges because by convention those are the ones that move. The red dots along the bottom will show the average motion of them. So when we've got a conductor like this, it's got a lot of red dots, and they are moving around randomly. And you can see that random motion produces a zero average motion. If you remember back to chemistry, this random motion has to do with the temperature of the substance. Well, when we attach a potential difference across this conductor, what we create in it is an electric field. And the electric field here is E, and it's represented by this arrow. This conductor helps concentrate that electric field, causing the random motion of the charges to be more in the direction of the electric field, since they all feel a force in that direction. Remember, that's our definition of an electric field, an area where something charged would feel a force. And so they start moving more in that direction. And look at that average motion. So they start off with no motion, no average motion. You establish the electric field and you have an average motion. And that average motion is what we call current. The collisions between the molecules that you can see here as big jumps in directionality is actually how the energy is transferred down the wire. All right, I've got a little video here to talk about Ohm's law. Ohm's law, as it will be explained, and then we'll come back. So see you in a minute.
Let's discuss a simple electric circuit powered by a battery. Chemical reactions inside a battery produce a certain potential difference of voltage across the battery, say 6 volts. This voltage produces electric current in the circuit connected to its terminals. One terminal is positive and the other negative. Which is not important here. The current in the light bulb depends on voltage produced by the battery and the resistance of the light bulb. So it's important to distinguish among voltage, current, and resistance. Voltage is energy per charge, a sort of electric pressure, measured in units joules per coulomb, which we call volts, symbol capital V. To say a battery is 6 volts means that every coulomb of charge passing through the battery is given 6 joules of energy. Current is the flow of charge per second, usually electrons, produced by voltage. Current is measured in coulombs per second, which we name amperes, or for short, amps. The symbol for amps is a capital A. Suppose the current is 3 amps. Carrying 3 amps means that every second 3 coulombs of charge flow through the wire. Energized electrons flow from the battery through the circuit where all that energy is dissipated and back through the battery again to be re-energized. If a break occurs anywhere along the circuit pathway, current ceases. The direction of current in this simple circuit is not important. Some terminology. Charge flows through a bulb, so we say there's current in a bulb. Voltage is established across a bulb. Voltage doesn't flow, charge flows. Resistance is a property of the substance through which the electric charge flows. Very little resistance in copper and a lot in rubber or plastic. Electric resistance is measured in ohms. The standard abbreviation for the ohm is Greek letter omega, like the song Om, Om on the Rain. Resistance is where energy is converted to heat and light. In this single bulb circuit, most all the resistance is in the bulb's filament. Here we're considering an incandescent bulb, less common now but still around. Here's the symbol for resistance. We ignore all resistance in the connecting wires because compared with filament resistance in the bulb, the resistance offered by the wires and battery interior is negligible. A bit of history. Early in the 19th century, a German scientist and teacher, Georg Ohm, discovered a relationship between current, voltage, and resistance. He found that the amount of current in a wire is equal to the voltage across the wire divided by its resistance. This is Ohm's law. Current equals voltage per resistance, where I represents current, V represents voltage, and R represents resistance.
All right, you're back. I want to have another little simulation here where we have a very simple circuit. We have something that has resistance, something that takes extra energy to get through. And then we have our voltage source, our potential difference. And this is a more typical arrangement of Ohm's law. V equals IR, nice and a linear, no fractions to worry about in there. And the main thing I wanted you to realize here is that as the different parts of the law increase, like as I increase the voltage with keeping the resistance constant, or I lower the voltage, you can see how that has a direct relationship on the current. And then with the resistance, as I raise the resistance or lower the resistance, you can see that has an inverse relationship to current. So the bigger the resistance, the smaller the current. Smaller the resistance, the bigger the current. Voltage is the opposite. The smaller the voltage, the smaller the current. Bigger the voltage, the bigger the current. So those relationships both of those are with the current. The current is the one that is really created by this potential difference and the resistance. The potential difference being created by the battery or the power source. The resistance is a physical characteristic of this material in the circuit. And that physical characteristic can change. The way we describe the physical characteristic that creates resistance is something called resistivity. Resistivity is a physical, I don't want to use the word characteristic again because I've just used it like 10 times, but it's a physical property of the substance based on the arrangement of the electrons in the substance. So like metals have a very low resistivity because they have a lot of electrons that are very easy to move. Something like plastic or a rubber or something that would have a higher resistivity because they would have less electrons that are easy to move. The resistance is created by that resistivity, which is rho here, the length of the conductor, L, and the cross-sectional area, which is the circular area here in our simulation. So if I increase the resistivity, I increase the resistance of the wire. You can see that direct relationship. All right. And that is actually physically changing the material. So maybe I've got copper or platinum or gold down here, and now I've got a hunk of wood. So that is the resistivity is based on what the substance is made out of. The length, as I increase the length, I increase the resistance. That's that. There you have again a linear relationship. Decrease the length, decrease the resistance. With the cross-sectional area, I have that inverse relationship where I increase the area and I decrease the resistance. This is actually, since a lot of the current goes through the surface area, the outside, this is related to that. But what you really need to know and concentrate on is that they have that inverse relationship there. All right. Now, the next section that I wanted to talk about is power, electrical power. And here's another little clip that does a really good job explaining it and explaining some of the equations in it. So here you go.
And both bulbs glow with the same brightness. Brightness involves the energy emitted by a bulb, more specifically, the energy emitted per unit of time. Now we're talking about power. Recall that power is the ratio of energy per time. From the definition of voltage, energy per charge, we rearrange it to express energy as charge times voltage, and with substitution get power equals charge times voltage all over time. But charge per time is current. So we get power equals current times voltage. In shorthand notation, we say P equals IV. What's the power output of each bulb? It's P equals IV equals 3 amps times 6 volts equals 18 amps volts. And units amps volts equal watts. 1 amp times 1 volt equals 1 watt. So the power output of each bulb is 18 watts. What power does the battery supply? 6 amps times 6 volts gives 36 watts. And sure enough, if we add the power in each branch, 2 bulbs put out 2 times 18 watts equals 36 watts. Check. Let's change the resistance of one of these bulbs. Let it be 3 ohms. Then the current, 6 volts divided by 3 ohms, is 2 amps. Will it glow brighter, dimmer, or glow the same as the 2 ohm bulb? What's your answer? Did you say dimmer because less current at the same voltage means less power? If so, yum! And how much power is emitted by the 3 ohm bulb? Power equals 2 amps times 6 volts, and that's 12 watts. We can see that 12 watts is less than the 18 watts of the lower bulb. So the top bulb is dimmer than the bottom bulb. Does this all make sense? I hope so. There are other equations for electric power. Let's take a look. From P equals IV, substitute Ohm's law for I, and we have P equals V squared over R. Yum! Or substitute for V, which Ohm's law says equals IR, then P equals I squared R. So we have three equations for electric power.
All right, we're back. We have another simulation here where we have a battery and it's hooked up to a very simple resistor, and we got kind of a whimsical way here to show the amperage. These would be charges or electrons moving. What I wanted to show you here is what happens to the power. The resistor is going to dissipate power, in other words, use up electrical power, while the battery supplies it. So as the battery supplies voltage, that creates a current, and that charges start moving, and that makes them have to give up energy as they go through there. They have to dissipate power, and that comes out actually in a lot of cases as heat. If you put your hand over a standard incandescent light bulb, there's a lot of heat going on there. And think about back to your Easy Bake. If you ever had an Easy Bake oven, that's how it worked. If I increase the resistance, or if I decrease the resistance here, I get a higher current and I get more power. You can see how the temperature of that goes up. Increase the resistance and I get less current, less power. But on the same side, if I increase the voltage, I get more current again and more power. Since power is not only how much energy they have, which I increase by the voltage, but also how many charges go through there every second. So it's the energy per second. Current is the energy per charge, as you were just shown, and the voltage is how much energy each of those charges has. All right, in the last part here, I wanted to look at our equation sheet and go over some of the equations in this section. You've seen a bunch of them, so I'm going to go down to the third page here, and we'll make that a little bit bigger. And where we're really looking at is this box right here in the center. See if I can get it to fill the screen. Oh, I went a little bit too big. There we go. And now we'll bring it up to the top. So here's our power equation. Power is that voltage times the current, and then these are the other forms of it. So notice they're all equivalent. Use the form that best suits you. There's how resistance is related to the material that makes up the resistor. R is resistance. Rho is your resistivity, the type of material, length of it, and the cross-sectional area. As you read, you will find one section that I haven't talked about that's in your reading is that the resistivity of a material is related to the temperature of the material. So look at that section. You may want to look at it ahead of time and ask some questions in class, or ask a question about it at the end of the video. We have Ohm's law up here, how I traditionally write it. The change in voltage equals the current times the resistance. Voltage being in volts, current in amps, and R in ohms, as was discussed in the video. And then over here you just have the definition of current, that it's the amount of charge that passes by a point during a certain amount of time. The standard here is coulombs in seconds, which gives you amperes, or amps for short. So there's the equations. This is all in chapter 27 is what we're looking at, and I'll see you in class.